Sure. So, Tejaswini, I will advise you can start the presentation. Others can join.
Oh, okay,
Sure.
sure.
As people will join, I'm also. I have started the recording also. So, anyway, recording is getting shared.
Okay, good. Great. I'll just share my screen. Can you see my slides?
Yes, yes. Slides are visible.
Okay, so this session will be in continuation with the previous session. So, just to give a quick recap, uh, it was about designing lead code, and here we, listed the functional requirements like authentication, need a code editor, problem repository, uh, searching problem, solution repository, and many other peripheral modules like performance statistics, discussion forum, etc. And then we discussed about non-functional requirements. We assumed the scale of the problem, what would be the scale, uh, 10 million total active users, and then what part of the system would be write-heavy system and what part would be read-heavy system, how many codes runs per second, what could be the latency. We were okay with 1 to 2 seconds of latency because uh, some of the problems might have like hundreds of test cases to run. And then we discussed about reliability and availability of the system. We also did some back of the envelope calculations for problem repository, solution repository, and based on the amount of data that we stored, and the kind of query that we would do, we ended up choosing document database for the problem repository. Uh, our back of the envelope calculations for solution repository, we ended up storing our uh, video storage in blob storage, and again choosing document database. We also discussed about sharding. We arrived at the conclusion that consistent hashing would be a good approach there because it will be easier for us to handle peak load. And since we are using the NoSQL database, also consistent hashing is something we can leverage. We discussed about consistency. We discussed about availability zones, how many zones we will be required, how we will do our backup and recovery, and then we went on into what was the architecture that we would choose. We said we would choose a microservice architecture. We had the reasoning because it's easy to scale, maintain, isolate faults, isolate faults, and it actually fits well in a containerized architecture. Then we looked at into different modules, authentication services, what are the different services within that, what are the services within the search service. We went into detail the problem repository services. Uh, we defined our APIs. This is how our API looked like, and then we went into defining our database schema, and then why we will use a NoSQL, uh, and we had a discussion about whether SQL or NoSQL. Similar discussion for solution repository where we discussed about different APIs that this module would require, and then how the schema would look like. Again, discussion on whether we will choose a NoSQL or an SQL database. And yeah, and finally this separate test case DB, which we discussed that we will go for an SQL database because we need strong consistency. So this, until here, we had discussed in our previous session. So today we will deep dive into the core of this problem, which is code execution. So if you remember when we defined our non-functional requirements, we said that it would be the number of executions per second would be around 5,000. So the main problem here is how to handle this kind of scale. So let's deep dive into this. Uh, so code execution services here, the user is allowed to choose the language, update the language, submit the code, compile the code, and run, verify the results, display results, should be able to comment. All the users, others who are authenticated, should be able to comment on the solution, and then upvote or downvote. This is how our APIs would look like. We have save solution where we would uh, send our solution text, the language that the user has shared, and then there is an option to run the solution. And this is the API to run the solution. So the solution ID that we would receive from the previous API, we would use that to run the solution. And then if you want to update the solution, a different API, then an API to verify the solution. These are all additional APIs to retrieve the submission history and then resubmit. This resubmit and update are similar, so we can ignore that. The next one is grading the solution, then upvote the solution, downvote solution, and comment the solution. So these are the APIs.
Yeah.
Now,
Probably we can merge here the upvote and downvote with the flag saying true or false for upvote or downvote. So with
mm,
vote API, you can kind of take care of, yes.
yeah, correct. Yeah, that will make it simpler and generic. Okay, yeah. So the flag, whether it is upvote or downvote, you can make it just vote solution.
Right.
Okay, now moving on to the database design. So, uh, whenever a user submits or submits the solution, we will have to have a problem ID for which problem that the solution is. This is the solution user solution ID. So this is internal, specific to the particular user. It is not the solution ID, the generic solution ID, but it is user specific solution ID, just to identify, because the user might submit multiple solutions for different problems. So just to identify that, this is the user solution ID. And then result value, time consumed, memory consumed. So similarly, so this will be for one set of solutions and this will be for another set of solutions. Here I have again assumed that I would prefer going with a document DB, because every time we will be, querying for this set of, the complete set of details would be required. So based on locality of reference, it becomes easier, and then scaling also becomes easier. And the, because it provides a flexible schema in case in future. So this is an additional case that I have added here, this part of the slide. So say the grading and the voting requirement came later in the phase of the development. So in case of a document DB, I mean, we have some flexibility on changing the schema. So we have two options here actually. One option is you can use the existing document DB and add these values, and have them filled in this database. But there is a property of these votes, it is the number of votes that counts, right? So up vote and down vote. So it's like, the values are incremented, and the question was, is should we use a separate SQL database, a light database to just for these values? So this decision again depends on what kind of system we want. So either one option is use the same DB, because if the schema is flexible, you can use the document DB and add the upvote, downvote, and graded values. Or the other solution is we can have a separate table with this user ID, solution ID, grade, upvote, downvote, comment ID, because uh, you know say for example the solution is more sorted and there are a lot of upvotes and downvotes and grading, so it becomes optimal to update the database. And then sorry,
Yeah, your
screen.
screen sharing got lost. Okay,
Yeah,
can get it. Now it's back. Yes, go ahead.
okay.
Right. Few questions I had here.
Mhm.
First thing is, did we discussed about what was the number of users we are expecting, or
Oh, yes.
uh, and yes, from that, what is the number of transactions per second we may have in the database? That's no, in the back of envelope calculation. Did
So
we?
we assumed like 10 million
Yes.
daily active users. Yeah. So that is around 100 active users per second,
Right.
right?
100 active users per second, okay? But
Yeah.
once a user is
But
logged in, he may be performing multiple problems, solving multiple
exactly.
problems, maybe looking into profiles, commenting, upvoting, downvoting. So, what is the number
Yes.
of transactions you expect a user will be performing every day?
Yeah. That is, we assumed 5,000 transactions per second. That is
Okay,
what we assumed.
but
Yeah, for the
uh,
overall.
yeah, is the transaction same as the database query? It involves one database query, or how many database queries one transaction will have?
One transaction is one database query. It can be
One
read or write.
database, right? So we have around 5,000 database queries per second.
Yes,
Are they read or
correct.
write? How many read and how many write?
So we assumed our read-write ratio. Let me go back. Okay, we didn't actually. Yeah, so one fourth of the users will be running the solution, and the rest will be other operations like searching, upvoting, downvoting, commenting, etc. So based on that, it is around 2,000. 2,000 queries per second will be right. That is code
Yes.
submissions, and remaining 3,000 will be reads.
Right, right. Okay, nice. So, so yeah, this is kind of both read and write system. We have to optimize
Hmm.
for both reading and writing,
Hmm.
right? So then we also discussed about using a document store, right? So we have various document storages, for example MongoDB, Cassandra, and there could be multiple options. How can we optimize the read and writes in these databases?
Okay, so Reading would be as you said, we have multiple options: MongoDB, Cassandra. With Cassandra, um, we can have write replicas and read replicas. One is
Yes,
that solution.
yes.
Yeah, one would be that. The other would be one. I mean, when we use these JSONs, I think automatically read optimizations will happen. Like we are reading uh, reading it together, right?
Yeah.
In terms of yeah, for writing, since we are using different replicas, uh, okay, I'm not able to think about something else that we can do for optimizing read and write.
Correct. Okay. See, few suggestions I have here. So,
Hmm?
for some of the data, for example, maybe some user inputs, user information, or some information which is related to financial transactions and all, we can use
Mhm.
relational database. But
Hmm.
for many of the data, we may have to use some document database, because you have a lot of semi structured information,
Hmm.
and you need also high throughput and low latency in getting all these data, which could be around questions and around the submissions and solutions of the users. So some
Yeah.
NoSQL database like MongoDB could be one option, or Cassandra could be one option, or DynamoDB could be one option.
Hmm.
And we have to deal with large volume of data also, because a lot of code will be submitted by users. And you already said we have eventual consistency, so you don't need to be having the highest consistency level. And
Hmm.
with less consistency you can get faster read and write.
Hmm.
And caching could also be used to take care of the reads. And for
Yeah.
writing, you have only one way to have multiple nodes where you can write, and then you have to sync the data.
Hmm. 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 Okay. Yeah.
Yes?
For read, as you said, we can use CDNs, we can use caching, and we can uh, have read replicas and document database.
Yes,
And
yes.
right, we can have SQLs, like for example, this is like transactions will be high. Like this looks like transactional. So upward, downward. So we can have this as a SQL database, and then we can read it, and we can have multiple nodes.
But yeah, upvoting and downvoting may be happening very frequently. That could be the most
Mm.
highest number
Yeah,
of times or most frequently used transaction, upvote and downvote.
correct.
So,
Yeah.
how can we optimize this upvoting and downvoting so that there are less database connections?
So that there are less database connections. Okay. Uh, yeah.
Because,
So we can have yeah, caching. I think caching will help us.
okay,
Because it is eventual consistency is fine, and
right.
we can use like cache aside
Yes, you can write to
record.
the cache, write first to the cache and then to the database, right, at some periodic interval.
Yes.
This way, you can reduce the scale of database writing operation. Maybe a in-memory database could be used, or some storage which can cache the information, which could be Redis or Memcache, where you read and write the upvotes. And this is also not bulky information, this is just some number and associated with some comments or questions. So you
Yes.
can read and write to some in-memory cache and periodically update the database for
Yeah.
persistence.
I
Right.
have one question. If you're using like Redis, in Redis, is there a data structure like which increment like and decrement? Uh,
Redis is key value pair kind of database. So you can store any number of key value pairs, and you can use the key and update the various values. So
okay.
this
Something
way.
like the SQL provides like auto increment.
Okay. With respect to increment and decrement, how
Yeah.
to do in Redis?
Yeah.
I do believe they support atomic increment and decrement operations.
Mm-hmm. Mm-hmm. Okay.
Right. Let me just try recalling it about.
Sure. I recollect they have sorted sets, hashing, but yeah, if it is present, then it would be a huge advantage.
Just a minute. Yeah. J- right. So yeah, in Redis. Just a minute. Sorry. So yeah, we were discussing. I just got a call, so just got muted. So in Redis, you have for numerical values, increment and decrement commands. So
Hmm.
you can, yeah, you can use these commands to set some key and increment, decrement the value of that particular key.
Hmm.
Right, the value of that particular key, and could be incremented and decremented.
Okay. Okay. Yeah, that will help.
And you do have increment by for bulk, means increment by
Mhm.
bigger number instead of one.
Okay. 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 Yeah,
Because
something
this
like
is
the key can be. Yeah, the
yes,
key can be user solution that we has with uh,
correct,
you
because
know. Hmm.
see here, upvoting and downvoting, why we need increment and decrement operation is because this is many people may be simultaneously upvoting and downvoting a
Hmm.
particular question, right? And if there is a high concurrency, it may
Hmm.
happen that you may miss out some upvote or downvote. If
Hmm.
many, say, assume there is a new question which is a very popular question, and thousands of users are viewing it, and multiple of them are upvoting, downvoting it at the same time. So if you use the increment and decrement commands of Redis, then it will ensure that these commands are executed with high concurrency, and efficiently they are executed, because you may have a cluster of Redis servers in in your uh, in your infrastructure, so these
Yes.
operations will be fast.
Yes. Yeah, that would, I mean, dramatically increase the efficiency.
Correct. Perfect. Yeah,
Uh,
we can move on. So this was a little bit we went into the low level design as well, like how we will
yeah,
implement upvoting and downvoting. But yes, I believe this was an interesting point which we discussed. Go ahead.
yes. Okay, all right. Now, let us move on to the heart of the design, which is managing code submission.
Yeah. Can
But
you
before
increase
that,
your size
yeah,
of the
oh,
window?
the- yeah, yeah,
Yes, that's perfect.
yeah,
Now,
yeah. So let me just give a brief of how the high level design will look like. So we have our users here, and we have the API gateway, which will send the particular request to different to the respective servers, and the respective services will access the databases and give back the solution. So we have authentication services, problem set services, search services, and then the code run services. For the code run services, we will use in-memory cache because we need to execute it quickly, and even the solutions are popular solutions are kept in the cache. We will also be, so this problem has a lot of static content present in it. For example, the problem set or the problem set, solution set, all these are static content, whether it is text solution or video solution. So the most frequently used, we will be keeping it in the CDN, and so that displaying becomes low latency. Uh, Now let's deep dive into this code run services.
yes. And
Here
even we can
I
keep
have,
have all the questions in the CDN,
yeah,
right?
all the
Because not too many questions, maybe
yeah, yeah, yeah,
2000,
correct.
few thousands of questions only, and few videos on few thousands of videos also only, so that each and every question can be delivered to the students with good experience.
Yeah, yeah, that makes sense. I think we also calculated the storage, so it is not that huge, 2 GB. So I think it will fit. We can keep them all in CDN. Okay.
Sure, go
So
ahead.
moving on deeper into this code run services. So here, basically, our code question here is how do we, execute 200 submissions per second, right? Synchronous execution is something which will not be possible. Uh, we have multiple approaches here. I will talk about two approaches, but uh, the first one is, the main code here is we have to schedule the execution of this submitted code, and it has to be scheduled in a queue. So for this queue, uh, how do we, architecture this? Either we can use the first approach is we can use a DB, which will actually do the job of a job scheduler, and for example we have a job id, and code id which it has to execute. It will be having the status, whether it is executed or queued or something. So we can use a small db like a scheduler. That's the first approach, and we can have multiple workers reading from this db and doing the corresponding actions. So, for example, if the job is not yet scheduled, and if the priority is high, then a worker which has to compile and run the code can read that particular job and compile and run the code. For a job ID which has been completed, a worker which would display the results can read it and then display the results. So that is one approach, using a DB. The other approach would be what I have used here, which is a PubSub system. The reason I have used a PubSub system is, one, because I can achieve some kind of asynchronous and synchronous processing, and I can improve the latency. In addition to that, I can add additional peripherals, like I have this grading, which uh, will also need the final results. I can the display results, which also requires final results. So basically, one output can be written by multiple different kinds of workers. So for that reason, I have used the PubSub kind of system here at the heart of this. This eventually is a event-driven architecture where events are registered and queued into the PubSub and read by respective workers on the other side. And using this model, scaling also becomes easy. So, for example, let me just go through the flow. Say the user has submitted the code, and the code is submitted, and event is generated, and this event say is in a JSON format, and it gets passed on to the PubSub. So we will have here multiple queues, or we can have multiple queues for specific activity. Say this queue code submitted to the event goes here, and this code compilation, which is the consumer of this particular event, will come to know, okay, there's a code submitted, and it will read that code and compile it. Once it is compiled, it is sent back a message that, okay, the code is compiled, and this event that the code is compiled can be read by our scheduled test case execution service, which will fetch the information on what all test cases have to be executed from our DB, and then it will schedule all those in another queue, which will be read by this particular service. Now, this is for one particular job, but in our system, we will have around 2000 jobs per second. So, every event can go into this queue, and asynchronously can be compiled, and test case execution can be, set, and the results can be passed. So when there are 2000 events happening per second, at this point of at this part of the system, you'll have to say maybe like one execution will have 100 test cases, so around, uh, it will be around, I would say, 200K submissions. So here we can have multiple consumers, we can have multiple workers that can pick from the same queue and execute all of these jobs. So, and that's how we can achieve scalability and reduce latency as well. So this is one use case where you can see that how asynchronous architecture would help in scaling. Similarly, for displaying results, uh, um, as soon as a result is present, an event is generated, and then display results services can read from it and give the data back to the user, and the same final result can be consumed by three other consumers. So it can be one is display results, one is the database where the user results are stored, and one will be the grading. So you can see that we have achieved some kind of parallelism here, and that again, because of asynchronous communication, and that again helps us decrease the latency. So yes, so this is kind of the event-driven architecture for scaled approach. Few of the things are, how can we handle dynamic code allocation? That is one question. So that is again, you can have again maybe a Kubernetes kind of a system where we have nodes for running, um, test case, and you can upscale and downscale as per the load. One important thing here is what happens when a job I would like to actually discuss two cases. One is what happens when a job fails, and the other use case is what happens when job is taking too much time, how the system will react. So, say for example, you have given a job for execution here, and it fails. So, the advantage of using a PubSub system is that if our events are idempotent, which is that we can execute that event multiple times without actually changing the state of the results, then PubSub system fits very well into that model. So say the job fails here, and so what happens is in a PubSub system, the job is the event is red. When the event is read, the PubSub actually waits for the acknowledgement that the event is executed. So when the job fails, the event comes back that okay, the job read is failed. So what happens is this message is kept in the queue to be read again. So maybe some other worker can pick that job and re-execute it. So that way, even if the job fails, we can make sure that the system is reliable because there's another consumer who can pick it, or the same consumer can recover and pick it and re-execute it and give the results. That is one case. The other case is what about if a job is taking too much of time? What happens is in a PubSub, generally there is a um, timeout set. For example, say like 10 milliseconds is what the timeout is set. This timeout is for how much time the consumer takes to read the message and process it, and send an acknowledgement that I have read the message and I'm processing it. Suppose the job is taking too much time, then there is and 10 minute second timeout is exceeded, then the PubSub will think that okay, this job is failed and let me give it to some other, make it available to be read again. So in that case, we'll have to do some additional kind of work where we can actually have another kind of a database, like a small database or a data place where we actually track uh, you know uh, these nodes, different nodes, as to what is the execution time of all the jobs that are taken. So we can have something like a monitoring system where it is trying to understand if the jobs are actually taking longer time, and if so, we can issue a kill command, and then we can reschedule the execution of that particular code submission. So yes, these two are the important scenarios that I thought should discuss. Uh, any questions here?
So yeah, few things. No, one is for storing the source code. We decided to use the blob storage, right? How are we storing the source code?
Yeah, source code. We decided that we will use the blob storage.
Right. And then we decided to use some containerized platform like Docker for creating
Mm.
the environments for running the code, right? Running the code
Yes,
and test cases, and then you will have a executor, job executor, that will be responsible for calling the Docker container and executing the code and then getting the result from there, right?
yes. So for example, there are 100 test cases for a particular code submission. So this is where those 100 test cases will get executed, and we will be aggregating the results and sending the final results.
Yes,
And this will be, yes, Docker based instance.
great. So I just got one question in mind, that assume some malicious user creates some viral virus code and it submits into Leet code. How can we ensure that we have proper security against these malicious code?
Okay. Yeah, for that, I think we can have malicious code. The highest chances, I'm assuming, it will be here when we execute. Say, for example, they are just overflowing the stack or continuously running and consuming the disk. So we can have for like a monitoring system, which will, you know, keep a track of how much time the code should execute, uh, the maximum limit for a code to execute, and then if it is taking more time, then we can kill it. So we can have a subsystem which monitors all this and takes actions, and probably disable, notify the admin, or have a notification system as well.
Sure, sure. Great. And one more thing about replication and backup. How can we ensure that
Yeah.
the data, the source code is backed up and is also replicated? Yeah.
Yeah. So here, the results and the code has to be backed up and replicated. So what I'm using here is I'm using databases and sharding them with respect to geography, and we can have the replication, have some lag in replication of 6 to 7 hours. Um, we are okay with so much of time for replication because um, the usual scenario is a submitter or a code, someone who is a user who's submitting the code would be specifically very local to his current location, maybe for example Asia, and it is okay for a user who is in US or any other location to actually have this solution seen after some time. Eventual consistency is okay. Worst case, if the user who has submitted the code is also traveling from Asia to US, that also takes a significant amount of time. So 6 hours is a good amount of time for the replication to complete. There are high chances that the user in US is going to see that code only tomorrow when he would wake up and see it. So it's safe to assume that we have good amount of time for replication. So so this way we can replicate data and make sure we have the backup of the data as well. We can have multiple copies again with replication factor 3 in different geographies.
Great. Fine. Nice.
Okay,
No, I don't have any
so
further questions.
mhm,
Yes, perfect. Yeah,
okay,
go ahead.
yeah, yeah. So finally, the this is a sample how the problem would look like, and sample solution how it is stored in the database. So we have problem ID, and then we have the title of the solution, difficulty level, description, then solution ID, problem ID, language, the actual code. Yeah. Yeah, so with that, we come to the end of the system design of the code. Any more discussions? Anything that we have to discuss?
I think we covered everything in depth, and know each and every aspect, whether it is the queue, message queue, or database, document database, how to cache, how to do upvoting, downvoting, and one more input I just had about is securing against malicious code. We can do some validations in the front end code editor as well to prevent some malicious code injection also, right? So
Okay. Okay.
that could be one measure. Another one is a docker containers are isolated environment, so they anyway provide isolation against any malicious code execution, because any damage will be specific to a docker container, and we can recreate the docker container if a docker container is crashed because of some malicious code execution. So that can be managed or taken care by the approach you suggested, by having a monitor or timeout. Awesome.
Even API, yeah, API delimiter kind we can have, right? If one particular user is doing too many submissions.
Okay, yeah, rate limiting. Rate limiting is also important, because maybe someone will submit some code multiple times with the
Hmm.
intention to crash or bring down our backend infrastructure. So you can
Yeah.
have some rate limiting with allows users to submit maybe one code every minute, or some limit could be there to the number of submissions. Yes, that's
Yes.
also very good point. Great.
Okay, so that is all I had.
Yes. Thanks for this wonderful presentation. And yes, dividing this presentation in two parts. And definitely, I'll share the recording, and looking forward for more such sessions.
Yeah, sure, definitely.
Great.
Thank you.
Great. Then have a nice day ahead.
Thank you. Have a nice day. Bye.
Bye.